Okay, so thank you everyone for joining us for this seminar. So this is the second event of a relatively new seminar series of the Ifac Technical Committee on Optimal Control. And today we have three talks on different aspects of data-driven methods in control. So the first talk is going to be of Pietro Tesi. Unfortunately, Professor Nali could not join us today. But Ying Li, her former PhD student, has very kindly agreed to give the talk in place of her. And then we will have the final talk by Florian Dörfler. So I think without further ado, maybe we still have like 30 seconds, but Tim, maybe you can introduce our first speaker.
Yeah, I'm very happy to introduce to you Pietro Tesi, who received his PhD in computer and control engineering from the University of Florence in Italy, where he's currently an associate professor. And he also holds a visiting position at the University of Groningen in the Netherlands. And his main research interests include adaptive and learning systems and data-driven control. And Pietro is an editor for the International Journal of Robust and Nonlinear Control and an associate editor for the IEEE Control Systems Letters. And without further ado, Pietro, if you want to share your slides, please go ahead. We are very much looking forward to your talk.
Do you see my screen?
Yes, now in full screen, looks very good.
Okay. Thank you for the introduction, and thank you and to Thulasi for inviting me. So I'm going to talk about certainty equivalent approach to LQR design. This is a joint work with Claudio De Persis from University of Groningen and with Florian Dörfler from Zurich. So this talk is about the linear quadratic regulator problem, or LQR problem. And well, the LQR problem doesn't need much introduction. It's a cornerstone of automatic control. And in fact, is one of the most popular topics in data-driven control. So you can find a variety of methods for data-driven LQR that can be classified as indirect versus direct, depending on whether you try to identify the system dynamics from data, or as certainty equivalence versus robust, depending on whether you explicitly take into account uncertainty in the data. So this talk is about the certainty equivalence LQR, and we will understand soon what I mean precisely by that. And in particular, I will give a new formulation of this certainty equivalence control, which is a direct and, let's say, regularized formulation. And I will discuss also how to blend certainty equivalence with robust formulation, which gives us a tool to trade off performance and robustness. So why we like this new approach? Because we think that this approach not only gives interesting results for what concerns LQR, but we think that these results, these ideas, can be relevant also for other multi-objective problems where performance and robustness coexist. So what I'm going to discuss here is available in that paper with Florian and Claudio. And I mentioned also these other two papers from which we borrowed many ideas, and in fact, which we combined together to get these results. So the first is a paper by Claudio and myself, and the other is a paper by Florian and Jeremy Coulson and Ivan Markowski. So briefly, outline of this talk. I would like to start with the formulation of the problem and to briefly recall what I mean by certainty equivalence. Then I would like to discuss the direct formulation of certainty equivalence control. And finally, to provide a direct and regularized formulation of certainty equivalence LQR and show how this is amenable to be blended with robust design. So let's start with the problem formulation. So we consider a discrete time, linear, and time invariant system in this form, where the notation is pretty much standard. X is the state, U is the control input, and D is a disturbance, is an external signal that enters the system. Z is a performance signal of interest, which takes into account both the state and the input. And this performance signal weights the relevant importance between X and U via the matrices Q and R. A and B is assumed to be stabilizable. And the problem of interest is to design a controller that makes the closed loop system stable and minimizes the H2 norm of the transfer matrix between the disturbance and the performance signal. Here I recall the H2 norm is the expected root mean square value of Z when the input is the white process with unit covariance matrix, which is the classic stochastic LQR formulation. So this is the typical formulation of the linear quadratic regulator problem. So it is known that the controller minimizing the H2 norm, which let me call it optimal, is unique and can be computed by solving a discrete time Riccati equation. But alternatively, and this is the formulation of interest to us, the optimal controller can be computed by solving the following program. Basically, we minimize the H2 norm, which can be expressed in this way, through the trace of this quantity here. And in fact, this formulation is usually known as the trace formulation, subject to a stability constraint. Now, typically, this constraint comes with the equality, and in this case, P is understood as the controllability Gramian of the closed loop system. But we can show that we can, without loss of generality, use an inequality. And this is convenient because it makes it possible to cast the problem as a semi-definite program after a change of variables. And this is the formulation which is of interest to us. So finding the optimal controller is easy when the matrices A and B are known. But we want to compute the optimal controller when A and B are unknown, and we just have access to a finite stream of data, possibly noisy, that are collected from the system during some experiment. What I mean is that for this system, we apply a certain input sequence of T samples, and we collect a measure of the state response. Those are our data. This is our data set. And the data can be noisy because this data might be generated with some unknown disturbance D. This is the formulation of what we mean exactly by data-driven LQR. So let me discuss briefly what I mean by certainty equivalence. Essentially, the certainty equivalence approach is an approach where we, in some way, identify the dynamics of the system from data, and then we apply the optimal design to this model, treating the model as the truth. And this can be done in the following way. So we now have this bunch of data, and we notice that this bunch of data satisfy a certain database relation. We take the first sample, we have x1 equal to ax0 plus bu0 plus d0. And then we continue with the second bunch of samples, x2, ax1 plus bu1 plus d1, and so on. And this gives us a database relation in compact form, which is of this type. Capital X1, which is this matrix here on the top, is equal to A, which is unknown, capital X0 plus B, capital U0 plus capital D0. which can also be written, this is a simple rearranging the terms in this way. And then we simply estimate the matrices A and B through an ordinary least square. So we solve the following minimization problem where the subscript F stands for Frobenius norm, and we get this solution. And this solution is takes the form x1 and the pseudo inverse of u0 x0, which is a solution, and this is the solution whenever the matrix u0 x0 has full row rank, because under this condition, the solution is unique. And notice that in general, this can be understood, and I will refer to this as an identifiability condition, because when the data are clean, having u0 x0 full row rank is in fact a necessary condition to identify the system matrices from data. Then the certainty equivalence approach is very simple because essentially solve the LQR problem, but we replace the true matrices A and B with the estimate, obtained via this least square estimate. Now, the standard certainty equivalence LQR problem is indirect. It's formulated as a bi-level problem that consists of a sequential system identification. We first identify the system matrices, plus model-based LQR, where we treat the model as the truth. Well, it turns out, and this is the interesting part, that the certainty equivalence LQR can also be cast as a direct program. And this comes with a lot of interesting consequences. But let's see first this direct formulation of LQR, and in particular of certainty equivalence LQR. Now, let's continue to assume that the matrix U0, X0 is full row rank. Then for any controller K, no matter which controller I pick, I have this relation satisfied. So I have A plus BK. I can write A plus BK as BA times the matrix Ki. And now the matrix Ki, I can express it in terms of the data U0 at 0 multiplied by a matrix G, where this matrix G solves these systems of equations, which has a solution because we are assuming U0 at 0 is full row rank. And now, as a last step, if I recall the database relation, so x1 is equal ax0 plus bu0 plus d0, and I plug this equality here, I obtain that I can write equivalently as a plus bk as x1 minus d0 that multiplies g. So this is a parameterization of the closed loop system. And for this reason, we call it direct because we use data not to identify the system dynamics, but to write directly the dynamics of the closed loop. And notice that this is valid. I can do that for any controller K. Yeah? Then the idea is pretty much simple, in the sense that instead of having A plus BK here in the model-based formulation of LQR, I can replace A plus BK with this quantity, coming from the previous calculation. X1 minus D0 that multiplies G, comes directly from this relation. And this formulation is equivalent to the ideal model-based formulation. With the problem that I don't know the matrix D0. And this comes the direct certainty equivalence formulation. Since D0 is unknown, so I cannot solve this problem because I don't know the matrix of the disturbance, one possible approach is to disregard D0. So to solve this problem, setting D0 equal to 0. And this amounts to enforcing some sort of certainty equivalence, because the design is carried out by treating the noise as zero. So as if there is no noise. So as if there is no uncertainty. And it turns out that, a variant of this program is in fact equivalent to the certainty equivalence approach. And this is stated in this theorem, which says that if we solve this problem by treating the noise as zero, so here we put zero in the stability constraint, then this program, where notice that I just added one additional constraint, is in fact equivalent to the certainty equivalence approach. And this formulation is direct because there is no intermediate identification step. And the proof is simple. We can look at the proof. The second equality constraint, so the last constraint, imposes that G must belong to the image of the pseudo-inverse of U0 x 0. And the first equality constraint tells us that G must therefore take the following form: pseudo-inverse of U0 x 0 that multiplies Ki. But then if we substitute this expression in X1G, we find that this expression takes the following form, where the first two matrices is actually nothing but the least square estimate. So we obtain that this equivalence between this direct and indirect formulation of LQR. So why this direct formulation of LQR is interesting? Because this gives some a lot of intuition regarding the robustness properties of the certainty equivalent solution. In particular, now we can claim that the certainty equivalent solution enforces this inequality. And we know that the stability condition, so the condition to get stability, is this one, where we have this D0 appearing. So for stability, of course, we would like that our solution can somehow mitigate the effect of the disturbance D0. And we see that the certainty equivalence approach is capable of doing that up to some extent, provided that the signals that we measure are of good quality. So provided that the signal-to-noise ratio is sufficiently large. In particular, define the signal-to-noise ratio as this quantity here, where sigma min stands for minimum singular value, sigma max stands for maximum singular value. So the signal-to-noise ratio is the ratio between useful information, what we measure, state and input samples, and useless information, the noise. Well, we can see that as the numerator increases, the norm of G gets smaller. And if the norm of G gets smaller, the effect of the matrix D0, so the effect of the noise, becomes smaller. And we can formalize this intuition. Now the result is slightly technical, but essentially this result says that as long as we have data of good quality, the certainty equivalence approach works very well. In particular, it says the following. Let define by this quantity the cost obtained by our solution. Our solution denoted by K bar. And let this other quantity, K opt, denote the cost coming from the unknown optimal solution. This theorem, this result, says that you fix a desired suboptimality gap, so a desired gap from optimality, then the certainty equivalent approach is capable of meeting this gap as long as the signal-to-noise ratio is sufficiently large. So in particular, this is an epsilon delta type of result which says that for any epsilon, so for any desired suboptimality gap, there is a value of the signal-to-noise ratio such that if the signal-to-noise ratio is above this quantity, then the certainty equivalent approach can meet this gap. So this confirms what we can observe in simulation, so that when the data are of good quality, the certainty equivalence approach works very well. And we can actually strengthen this result beyond an epsilon delta type of result, because if we do some math, and here the details are in the paper, we can find the following. So we can quantify a threshold for the signal-to-noise ratio, above which the suboptimality gap scales as the inverse of the signal-to-noise ratio. So scales linearly as the inverse of the signal-to-noise ratio. And it is interesting to observe that the same scaling is shared by the estimation error. So we can rephrase these results by saying that as long as we are in regimes of small estimation error, the suboptimality gap scale linearly with the estimation error. And this is a result that aligns with recent results on LQR, but this result is independent of the noise statistics. Because notice that I didn't say anything regarding the distribution that the noise must have in order for these results to hold. Okay, here is a simple example. We take a linear system. We choose the weights in the following way, where we don't penalize much the input because we don't want to restrict the search to low gain controllers. And this favors finding stabilizing solutions. And we test the certainty equivalence approach in 100 trials, each time using 20 samples. And we take input and disturbance to be normally distributed, but it also holds with other patterns, so the same conclusion. And the simulation results confirm what I was saying before. So as long as you are in regimes of small uncertainty, so in regimes of good signal-to-noise ratio, certainty equivalence perform extremely well. This is, let's say, expected from numerical simulation, and in fact, this is what also the theory tells us. As soon as the signal-to-noise ratio drops, the performance deteriorates, and in particular, we don't even always find stabilizing controllers, and I will discuss this point in a moment. We can make some other observation, also partially inspired by the example. I didn't say anything regarding the amount of data that we need to get these results. Well, and in fact, the only constraint that comes from our result is that the matrix U0 X0 must have a full row rank. And these conditions requires at least a number of samples equal to the dimension of the state plus the dimension of the input. But this means that even n plus m samples may be sufficient. And this is an interesting point because this stresses effect which is often overlooked. And the fact is that the quality of the data counts more than the quantity of the data. We can also expand these results in other directions. So, for example, we can also extend these results or make it more specific to cases where we know better about the statistics of the noise. And this is a case where it might be convenient, in fact, to collect large data sets. For example, if we know for some reason, we have information about the fact that the noise entering the system obeys the laws of large numbers, meaning that it's a zero mean noise concentrated or is concentrated around the mean, then we can perform multiple experiments. So we can perform the same experiment on the system multiple times and then averaging the data. And this allows us to filter out noise. And we can exploit, in this case, also many results available in non-asymptotic statistics, so concentration bounds, to get some high confidence results in regarding the value of the signal-to-noise ratio and regarding the norm of the energy of the noise. And essentially, we can get high probability results regarding the stability properties of the control. So this is about a direct formulation of LQR, and this direct formulation somehow gives us some intuition regarding the stability properties of certainty equivalence. We can do one extra step and link certainty equivalence to robust design. Why this is important? Well, it is known theoretically, and it is known also if you just do some simulations, that certainty equivalence can fail to return stabilizing controllers if there is too much uncertainty in the data. So, for example, if the level of noise is too large. And this has been the underlying motivation for the development of many approaches, many robust approaches to LQR that explicitly take into account uncertainty in the data. And basically, the idea is that starting from the least square estimate, we build a confidence region. This might be a ball around the estimate or an ellipsoidal region around the estimate that essentially tells us where the true system parameters might be with certain confidence. And then instead of applying the certainty equivalence approach, so instead of designing the controller treating the least square estimate as the truth, we apply a robust controller. So a controller that stabilizes the whole uncertainty region. And many approaches of this kind have been proposed based on the S procedure, based on system level synthesis, based on traditional tools from robust control. But then here the question becomes tricky because robustness comes at the expense of performance. Well, it turns out that the direct approach to certainty equivalence gives us a nice way to balance, to trade off smoothly between robustness and performance. And this is the idea. Recall the direct formulation of certainty equivalence, where we have here, we have the cost. Here we have a stability constraint, where we treat the noise, we set the noise to 0. So we regard the data as if the noise were 0. This is a constraint coming from our direct formulation, and the last constraint is the constraint that accounts for the least square fitting criterion. And to use a shorthand notation, let me call this matrix here, let me call it pi. So the last constraint, which is the least square fitting criterion, is pi g equal to 0. But then the idea is that instead of expressing this constraint as a hard constraint, we lift it to the objective function. So we express this constraint as a penalty in the objective function. So we move the constraint from here to here, where we have pi g here, and where we weight the norm of pi g, any norm, we weight with a parameter lambda, a positive parameter lambda. It turns out that this formulation is again equivalent to the certainty equivalence formulation, provided that the weight is sufficiently large. So, from a practical point of view, this is just a rewriting, but the interesting point is that conceptually, now we can view certainty equivalence as a multi-criteria problem that simultaneously account for identification, the new penalty in the function, and control objective, which is the LQR function. But then the idea is immediate that we can then consider other multi-criteria formulation. And for example, if you recall that the certainty equivalence solution enforces this, while the ideal stability condition is the one where we have noise, then a possible alternative is to blend the certainty equivalence with another stability promoting regularizer. So we add another term in the cost function where we penalize the norm of G multiplied by P multiplied by G transpose. So essentially we multiply this term here, which is precisely the term that multiplies D0 in the inequality that defines our stability constraint. And the idea is very interesting, and here are some numerical results that speak for themselves. Here we compare three approaches. One is the pure certainty equivalence approach. The second one is a robust approach where we penalize this GPG transpose. And one is the mixed approach where we blend certainty equivalence with this stability promoting regularizer. And we see that this mixed approach basically combines the benefit of certainty equivalence and the robust approach. Because in regimes of good signal-to-noise ratio, so of small noise, you see that the performance are very good, and they are close to the one provided by the certainty equivalence approach. But when we move to noisy settings, so when the signal-to-noise ratio is very low, highly noisy, we see that we have the benefit, we can combine the benefits of a robust controller because we always find stabilizing controller, but with a reduced error, suboptimality gap, compared to the error that we would obtain with a pure robust approach. In fact, we have almost a 100% improvement with respect to applying a pure robust approach. So I'm done. Just to make a short summary. So the certainty equivalent approach, which is best known as an indirect method, can actually be reformulated as a direct control problem. And this direct formulation is interesting because it allows for a simple statistic-free robustness and performance analysis. The interesting part is that this direct formulation can also be cast as a regularized problem, which is amenable to be blended with robust stability promoting regularizer. And as I was saying at the beginning, we believe that these ideas can be interesting beyond the LQR problem, and can prove relevant in other multi-objective problems where we have to balance between between performance and robustness. So I think it's there. So I would like to thank you for your attention, and I'm happy to take questions if any.
Thank you very much, Pietro, for a very nice talk. And thanks for also staying in time. And let me remind the audience, you can ask questions via the Q&A tab, and we will convey it to our speakers. And in the meantime, I would have a first question for you, Pietro. You've said you don't need statistics in order to do the design. But let me twist the perspective. Could you benefit from knowing some statistics of your noise?
Okay, that's this is an interesting question that I would reply as follows. So if you have information about the statistics of noise, then it might be in fact convenient to exploit it. I mean, there is no reason to not exploit it. And let me go here. It is known from non-asymptotic statistics that, for example, if you know that your disturbance has a normal distribution, then the energy of the matrix forming the disturbance scales with the number of experiments that you make if you average the data, because the variance scales as the inverse of the number of experiments. But the point is that what happens if you don't have this information, or what happens if you have some samples that do not comply with your, let's say, framework. So, for example, if you assume that the disturbance are independent and identically distributed samples drawn from the normal distribution, but what happens if you collect the data and for some reason the data show correlation or are dependent? Well, this result essentially says that things can still work and work very well, provided that the amount of noise, the energy of the noise is small compared to the energy of the data. So this is what I call it here a signal-to-noise ratio. So this signal-to-noise ratio does not use statistics. So this is a result that you can apply independent of the type of noise that you have. Of course, if you know more about the noise, then you can strengthen the results. It's essentially exactly in this sense here. I mean, all these results dealing with regret bounds or sample complexity analysis, you can continue to apply these results. But essentially here I'm saying that if these assumptions fail, well, you might still be able to have extremely nice performance.
Okay, thanks for the answer. We have a couple of questions coming in, and I would first take the one from Deepak Mandloy, who asked in the chat, what are the advantages in compared to instead we identify the plant first and then solve conventionally the LQR?
Okay, this is a very good question. And in fact, I think that in our community, there is too much debate between what is better between indirect and direct control. They are both, I mean, good candidates. And depending on the problem, you might have more intuitions from an indirect formulation or more intuition from a direct formulation. So here, I'm not in fact stating that the direct formulation has to be preferred to the indirect one, because in the end, all these results says that the direct formulation is equivalent to the indirect one. depending on the problem, it might be the case that one formulation gives you some more intuition on the problem. So for example, here from the direct formulation, I can see that to have some sort of stability, this matrix appearing here, this GPG transpose, must somehow compensate for the presence of the zero. And this suggests me that the certainty equivalence approach, in fact, might have a certain degree of robustness, and in fact, it has a certain degree of robustness, as long as the signal-to-noise relation is large enough. Or if we move to the regularized version, where I lift the least square constraint to the objective function, this formulation is direct and this gives me the intuition that I might blend this least square fitting criterion with other penalties and mix certainty equivalence with a robust approach, which is something perhaps less obvious in an indirect formulation. But I would not pose direct and indirect methods as a sort of fight. I mean, they are both valuable approaches, and depending on the problem, we might draw inspiration from both of them.
Thanks. And we have two more questions in the Q&A tab, and I would start, because you have directly the perfect slide for answering the question, from a question from an anonymous attendee who asked about the convexity of these advanced optimization problems for the mixed criteria. Yeah. Can you comment on, sure. Are we losing convexity here?
Yeah, absolutely. No, not at all. I didn't talk about it. You can find details in the paper, but this constraint can be easily turned into a convex constraint, where instead of minimizing the norm of GPG transpose, you minimize the norm of another matrix that upper bounds GPG transpose, and you can write this new constraint as a convex constraint through a Schur complement. But it was not enough 30 minutes to enter these details. But let's say that all the formulation that you saw here can be casted as a semi-definite program, in fact. So you can find all the details in the paper.
Thank you, Pietro. I have two more questions. I would try to see whether we can have quick answers and then move on in our agenda, not to jeopardize the schedule right at the beginning. Stefan Trenn, a fellow colleague from Groningen, asked, in the last table, in this presence of strong noise, the combined method outperformed both the individual method, while in other cases it was somewhat between both individual methods, what you kind of would expect. Can you comment on that unexpected outperformance?
Well, the point here, and cheers to my colleagues from Groningen, I hope you visit you soon, if the COVID allows. And the point is that I don't believe that there is the best solution in general, because I think you can always find a situation where one approach is outperforming the others. I think that LQR with noisy data is a prime example of the challenges that you might encounter in data-driven control, because data are noisy. The data are always noisy, so you need to enforce some degree of robustness. But on the other hand, you have a performance goal. So you need to balance between performance and robustness. So what is my experience simply in terms of simulations? Is that if you go for a pure robust approach, so if you follow the perspective here is my uncertainty. I try to stabilize the whole uncertainty set. What you get in the end does not resemble very much your optimal controller. You don't go even close, and you can see it here in the last column. The robust approach gives you 100% of stabilizing controller, but the median error is about 20%. So numerically, it doesn't resemble much. So you need somehow to balance, and this idea of regularizing the cost, so where basically you try to balance between performance and robustness, gives you a way to improve over a controller that looks purely to performance, which is the certainty equivalence, which fails to have 100% score of stabilizing controller, and improves also with respect to a purely robust approach. So it's something that makes you move smoothly between these two approaches. But I'm pretty sure that you can find numerical examples that suggest you that it is better to go for certainty equivalence, or another example where this suggests that it's better to go for a robust. I think that in the average case, I would go for a mixed solution, because gives you in most of the cases a reasonable outcome.
Okay, and I have one final question from Rafał Wisniewski from Aalborg, who has typed in the chat: do you use the data to formulate the involved matrices once, or would you repeat the process of formulating the matrices? And especially he's asking this in the view of the fact that the matrices are realizations of some random variables, and he's asking, how does this relate to our concept of stability that we are applying here?
No, okay. The concept is the following. So, in general, here these matrices comes from one single realization. So this is so the result given here does not involve multiple realization. It might be, but it's not constrained to come from multiple experiments. If you know that your disturbance, your noise follows some nice statistics. So for example, if you know that if you average the data, then you can improve the signal-to-noise ratio because you filter out noise, then in this case, in fact, all these quantities will refer to average matrices. So you carry out the design not using one single realization, but the matrices coming from averaging the multiple data sets. But I mean, from a practical point of view, it's just a matter to repeat one experiment multiple times, and then you average the result. So
okay. Thanks, Pietro, for answering all the questions. We have one remaining one in the Q&A tab. Maybe you can take it and type the answer in the interest of time, that we don't blow up our agenda right in the beginning. With this, please join me in thanking Pietro again for a very nice talk and an interesting discussion. And I would give the word back to Thulasi for introducing our next speaker.
Thank you.
Thank you, Pietro. So as I mentioned in the beginning, unfortunately, Professor Nali couldn't join us today, but we're very lucky to have Dr. Yingling Li here with us instead, and she will be giving the second talk. So Yingling received her PhD in applied mathematics at Harvard under the supervision of Lina, and she's currently a postdoc at the University of Illinois Urbana-Champaign, where she's working with Professor Jeff Shamma. She works on different topics in control, including online optimal control, learning-based control, reinforcement learning, and she's particularly interested in applications to smart grid, smart cities, and robotics. So Yingling, without further ado, I'll let you take the floor. Thank you.
Let me see. Can you see the screen? Yeah. Can you see the full? Okay, great. So yeah, thanks for having me here. And Lina wants me to send her apologies to all the audience for having some personal emergencies, so she couldn't come today. And yeah, so I will just give the same talk on behalf of her. So today I will talk about the learning-based control for constrained linear quadratic regulators. And I'll provide both safety guarantees and non-asymptotic regret guarantees. And this is joint work with Jeff Sharma at UIUC, Silver Das at IBM, and Lina at Harvard. So in many applications, we need to safely operate uncertain systems. Like in the drone, there may be model uncertainties, parameter uncertainties, but we still need to make sure that the drone do not crash. The same thing happens for the autonomous driving. And so if we only care about safety itself, it is not very challenging because we can be very, very conservative, like we move very, very slowly, or just put the drone on the ground, not fly it at all. The problem with over-conservative operations is that it gives poor performance. We are not going to reach the desirable location as we want, at least not reach the location in a short time. So how to reduce conservativeness? There is one popular way in recent years, which is to add a learning component to the safe control design. And by learning from the history data generated from the system, we can reduce system uncertainties so that we can reduce conservativeness and also improve the performance accordingly. Notice that here, when we design the controller, we have to fulfill 3 tasks. First, we need the controller to encourage exploration because the data generated from the controller will be used in later rounds to learn the system. So we hope that the data generated contains enough information for us to learn the system. And also, based on the learned, improved system, we want the controller to improve the system performance, which is called exploitation in the learning literature. And lastly, we need the controller to ensure safe operation of the system, so to satisfy the safety constraints. And those 3 tasks, the exploration, exploitation, and safety, are inherently conflicting with each other. Like I mentioned before, the safety, it conflicts with the exploration and exploitation because to guarantee safety, we want to be conservative. But if we are too conservative, we are not exploring the systems enough and we are not improving the performance. And also, even without the safety, exploration and exploitation are conflicting with each other. If we want to explore new areas, we may try things that may give us poor performance. But if we only do things that we know that are good, we are not exploring the new areas, so we are not gaining new information. So one major challenge we are facing here is that how to balance this exploration exploitation trade-offs while ensuring safety during the learning process. And this challenge is widely recognized in the literature and has received a lot of research interest in the past years. For example, from the control literature, there are many different directions of work, but here just as a brief review, I mentioned the safety certificate plus some reinforcement learning to provide both safety and also a good exploit trade-off. and also robust adaptive model predictive control, which guarantee constraint satisfaction, and also add some persistent excitation to encourage exploration. And the problem with those literature is that, so the good thing about those literature is that they can prove safety. They can have safety guarantees. But the problem is that they do not characterize the exploration-exploitation trade-off in a rigorous way. Especially there lacks non-asymptotic understanding on how the learning performs during the exploration and exploitation phase. And on the other hand, from the learning literature, there are a lot of work on the exploration exploitation trade-off and its non-asymptotic performance, like reinforcement learning, and also the recent research interest on learning-based LQRs, but without constraints. But in the learning literature, as I mentioned, they usually do not consider constraints, so there's no safety guarantees. And there are also some recent results focusing on both safety and the non-asymptotic trade-off performance. For example, this paper, 2020, they consider soft constraints. So it allows constraint violation during the learning process to a little bit, and also provide some regret guarantee to capture the non-asymptotic performance. And there's also a paper this year sent to arXiv a few months ago. They consider hard constraints and proves the regret. But they do not reduce the conservativeness on the constraints after learning new data. So like I said, there are very limited results on both safety and the non-asymptotic performance, and there is not a clear understanding on how to achieve both safety and a good non-asymptotic trade-off performance. So our goal is that we want to also try to do something, try to design some learning-based control, and we focus on hard constraint satisfaction. And also we hope to get a certain kind of non-asymptotic performance by reducing the conservativeness of the constraints after learning. And since this is a very challenging problem, we start with a rather simplified model, the constraint linear quadratic regulator. So here, so it's basically just a quadratic cost and a linear dynamical systems. And also we impose constraints on the state and actions. And those constraints are linear. So they define a polytope on the feasible or the safe state space and action space. And we also consider bounded disturbances. And we consider that we do not know the model, the A star and the B star exactly. So we will try to learn the model first. And then we apply the certainty equivalence as already been discussed in the previous talk. And based on certainty equivalence, we try to apply some optimal controller. And then we add some random perturbation on the random controller to encourage exploration. And so it also generates data along the way. And with the new data generated, we can improve our model. And with improved model, we can get improved controller based on the certainty equivalence, and this loop just goes on. And during this learning loop, we want to guarantee two things. We want to guarantee safety, which means that we hope that all the constraints are satisfied during the learning process. And we also hope to achieve optimal performance by balancing the exploration and exploitation trade-off. So it turns out that even for the constrained LQR, the problem, and even when the model A star and B star are known, the problem is already quite difficult, which is in stark contrast with the unconstrained LQR, where we can solve the Riccati equation to get a closed form solution. So the difficulty comes from the fact that even if the system is known, this constraint LQR does not have a computationally efficient algorithm to compute the optimal controller. So there's no closed form optimal controller, and there even no computationally efficient way to compute the optimal controller. So what people have been doing in the literature is that they sacrifice optimality for computation efficiency by considering policies from a smaller class, from with some good structures. For example, this paper in 2018, they try to compute a safe linear policy to optimize the constraint LQR by using the system level synthesis. And there are also robust model predicting control whose outputs are piecewise affine policies. And there are also control barrier functions which generate general nonlinear policies. And because even with a known model, we cannot compute the optimal controller. So a more reasonable goal for learning is that we want to achieve what is achievable with a known model, which means that we hope to achieve either the optimal linear policy or the robust MPC or the optimal policy from the control barrier function with a known model by using the learning tools to handle the model uncertainty. And for this talk, we'll focus on the linear policy design. And it is our ongoing work to work on the robust MPC. We have some preliminary results, but I'm not going to include it in this talk, but I'm happy to discuss it offline. And for control barrier functions, is left for the future work. So now I will talk about how to design a safe linear policy and how to adaptively update the safe linear policy to achieve a good exploration-exploitation trade-off. And before going to the details of the algorithm design, this is an overview. So remember that we are doing certainty equivalence, which means that we should know what can be done when the model is known. Turns out that to compute a safe linear policy in a computationally efficient way, we need to do reparameterization. We need to reparameterize the linear policy as a affine disturbance policies, which I will explain in the next slide. And but the point is that with this reparameterization, we can convert the constraint LQR to a quadratic program, so it can be solved efficiently. And then with an unknown model, we will do model estimation and updates. And then with the estimated model, we include a pure exploitation phase by designing a cautious certainty equivalence controller, which is the optimal safe controller, optimal controller that is safe for all the uncertain models based on the current model estimation. And then we'll do safe exploration plus exploitation by adding some random noise to the cautious certainty equivalence controller. And then after exploration, we collect the data so we can update the model estimation and so on and so forth. One tiny issue here is that when we update the policies after the model updates, we may suffer some constraint violation. So I will also talk about how to address this constraint violation during the policy updates phase. So this is the overview of the algorithm. Now let me discuss the details of each phase. And the first is with a known model, and by affine disturbance policy, it is basically a finite impulse response. And the H is the length of the memory, the impulse response we want to consider. And it determines how many parameters we have in the affine disturbance policy. And the MK is a matrix in front of the disturbances. And it is our policy parameter to be designed. And W is a disturbance. And so I'm not going to the details, but because this is quite classical results, but the point is that, sorry, the point is that with this reparameterization, by writing the UT as a linear combination of the disturbances, we can convert the constraint LQR to a quadratic program, where the cost function is a quadratic cost function, and the constraints are also polytopic constraints on the policy parameters M. And then with this knowledge bearing in mind, we can go to the case with an unknown model. And with an unknown model, first is how we learn the model. So here we do the least square. So we are using statistics, unlike the previous one, previous talk. And so this is the least square. And so here, one contribution of us is that we allow that the UT to be very general. So it can be anything, can be generated by a time varying policy, linear or nonlinear policy, has memory or not. So it doesn't matter. The only point is that with this policy, the system should be bounded, so it should not explode. And also all the noises in the system, including the exploration noises, added to encourage the added to encourage the exploration of the policy, so to encourage, to guarantee persistent excitation, and also the system noises, WT, to the linear system, they should be anti-concentrated. And by anti-concentrated, it roughly means that it should span over all directions instead of only one direction. And our result on the statistics side is that for any general policies, as long as it is bounded and the noises are anti-concentrated, we can show that the least square has such a non-asymptotic model estimation error bound. And so this square root of m plus n over eta bar of square root of t is known to be the optimal for the linear exploration policy. So what we have done is to extend it to the nonlinear policies. And with this, well, we can do model updates by least square and to obtain point estimator with estimation error. And the error bound is provided on the last slide. And then we will do pure exploitation. Remember that if the model is known, so A star, B star unknown, we can solve this quadratic program to compute a safe affine disturbance policy. So when model is unknown, then we the same idea as certainty equivalence, we just replace the known model with the estimated model. But to guarantee robust constraint satisfaction for all models that are around the point estimator with error at most RE, we need to tighten the constraints. And the constraint tightening is quite a standard. So it's based on the perturbation analysis of this quadratic program. So we omitted the details here. And the point is that the constraint tightening term is depends linearly on the model error RE. And then we implement the disturbance, the fine disturbance policy, and with the estimated W, and this W is approximated by this projection of the xt plus 1 minus the predicted next state based on xtut and the estimated system parameters. So this is pure exploitation by the certainty equivalence with robust constraint satisfaction. And then we do safe exploitation and exploration and exploitation. And to encourage exploration, we add eta t explicitly to encourage exploration. And as I mentioned, the only requirement we need for eta t is that it is anti-concentrated. And because we add this additional noise term, so we need to further tighten the constraints to guarantee safety in the presence of this exploration noise. And the tightening term is still linear with the size of the exploration noise. And then with exploration, we collect data, and then we do model updates, and then the loop continues. So one issue is that when we compute, when we update this policy and this pure exploitation policy and this safe exploration and exploitation policy, if we directly change the policy to the new one, we may violate constraints. And this is shown in this case. So the trouble we are having is that if we compute one policy that is safe to implement for all time and compute another policy that is safe to implement for all time, but when we switch in the middle and there is a small transient phase that may violate the constraints. And how to handle it? We use like a trick, which is also borrowed from the literature, is a slow variation. Because if we are changing the policy slowly, then we can almost use the time invariant policy's property to infer the time slowly time varying policy's property. So we just avoid a sudden change in the policy by slowly updating the policy from the old one to the new one. And so this is just a line from the M old to M new. And this we divide this line by k steps. So just in k steps slowly moving to the new one. And because we are doing slow variation and we want this slowly varying policy sequence can be guaranteed to be safe by the safety guarantee on the time invariant one. So we actually have an additional error caused by the variation, but it's a slow variation. So we need to tighten the constraint a little bit further and to account for the slow variation. And this variation is a gamma, linear with gamma. And gamma captures how fast we are varying the policies. And in this way, we finish the design. So we do model update and pure exploitation. And after we compute the new safe policy, we apply the safe transit algorithm to slowly update the policy to the new one. And in this way, we can guarantee safety both in the transition phase and also in the later phases. And the loop continues. And the theoretical results is that so we can guarantee recursive feasibility and constraint satisfaction. So I didn't I didn't include the details of the parameters on this. So basically, what we need is that the parameters, the algorithm parameters should satisfy some monotonic requirements, and also the initial model uncertainty should be small enough, and then we can have recursive feasibility and constraint satisfaction. And as a plus, what we actually have is robust constraint satisfaction, because our algorithm is robust to all the uncertain systems during the learning process. And then we characterize the non-asymptotic trade-off performance by regret, because regret is traditionally used performance metrics in the literature to discuss the exploration and the exploitation trade-off. And what we do is that we the regret is defined as the online performance, the online total cost of our learning algorithm without knowing the model, minus the optimal cost generated by the optimal linear policy. And our regret bound is t to the power of 2/3. And so compared with the unconstrained LQR, the optimal regret is known to be the square root of t. And our regret is worse than that, which is intuitive because we have we are facing a more challenging problem. We need to guarantee safety, and we also guarantee robustness. So we have a slightly worse regret. And another interesting thing is that for unconstrained LQR with robust stability, the optimal regret is t to the power of 2/3. So actually give us so give us some optimism that this t to the power of 2/3 is actually optimal for our problem. But we haven't, we still need to formalize the idea to prove a matching lower bound. Yeah, so it is our future work to prove whether this t to the power of 2/3 regret is fundamental for the algorithm with robustness and safety guarantees. And so as a quick summary, so what we designed here is a safe linear policy by learning, and we provide a non-symptotic system estimation error, and we also provide online performance benching, comparing with the optimal linear policies, and discuss the non-asymptotic regret. And we also extended this work to time-varying environment, which is later, which is here. And so you may have noticed that I didn't include the numerical results here because we are still running it. And unfortunately, we couldn't get it finished before today's talk. And but I'm happy to provide them after we finish them. And for the future directions, so one interesting question is how to further reduce the conservativeness, for example, by considering chance constraints instead of hard constraints, and also by designing like the constraint tightening terms in a smarter way, and also how to study the regret of the learning-based robust MPC, which is our ongoing work. And there are also other directions on how to do barrier functions with learning, and also how to whether softer constraints can give us better learning performance, and also what's the fundamental limit for learning, the fundamental trade-off between safety and performance, and also the time-varying cases with time-varying and unknown systems, and also even adversarial cases. So talking about the robust learning. And yeah, and that's all. Thank you. Any questions?
Thank you very much, Ying, for this very nice talk. especially considering also that you stepped in at the very last moment. So thank you very much for that. If there are any questions, if you can please write it in the chat, then we will take them. Maybe I can start with one meanwhile. So I have a question about the part where you were saying how you ensure that the transition between controllers happens slowly over case steps. I was wondering if you can say something about how you pick how many, how slowly. So how do you pick the number of steps needed to ensure that the constraints are satisfied?
Yeah, that's a very good point. So I didn't include the details here, but the point is that I try to increase the K slowly so that the gamma will decrease as the learning continues, so that we can tighten the constraints less and less. And so we reduce the gamma as the learning continues, which means we increase the K. And so to get the T to the power of 2/3 rate, regret rate, we increase the K to scale it as T to the 1/3. So just slightly increasing, in the T to the 1/3 way. But but this is for the regret analysis. If we only care about constraint satisfaction and the recursive feasibility, so as long as gamma is decreasing, so as long as K is increasing or non-decreasing, so it can be constant or it can be slowly increasing whatsoever, we already have the recursive feasibility and the constraint satisfaction.
Okay. And maybe just one question that if maybe you've seen it in simulation or when you observe it. So essentially you are learning online, right? So you're doing this iteratively. Do you see at some point that considering that the system is time invariant as well, that at some point you converge to some solution and maybe it's not necessary to continue the learning loop or not?
Yeah, so so you are are you asking like whether we should stop?
Yeah, so essentially, do you observe that there is enough to consider a certain, like a fixed, not a fixed, but a finite number of episodes, or you have to repeat this? Yeah, I guess it depends on the situation, but
yeah. So so that's a good point. So yes, in like although theoretically the better, the longer the better, but in reality, when we plot the plot, we may see that it almost converges. So so if the improvement between the neighboring episodes are close, so like smaller than certain thresholds, then it may be indicating a good time to stop, because at that time, even if we increase the learning horizon, then the marginal improvement is limited.
Okay, thank you. I see also two questions here in the chat from Andrea Iannelli. So the first question is, how are the lengths of the pure exploitation and exploration/exploitation phases decided, and what is the effect of this on the regret?
That's a very good question. So, so for the yeah, so first of all, this pure exploitation is only added for our T to the 2/3 regret. So again, if we do not care about regret, only the safety, then the length of them or whether adding a pure exploitation or not doesn't really matter. But now how to get the T to the 2/3 regret. And so to get that regret, our pure exploitation phase, sorry, let me start with the exploration phase. So our exploration and exploitation phase takes because let's suppose the episode length is t. So for example, this whole episode is t. And then exploration plus exploitation takes t to the 2/3 stages. So it increases slower than the episode length. And then the pure exploitation length is t minus t to the 2/3. So we spend most of the time exploiting and relatively less time for exploration.
Okay, thank you. And then the second part of this question, how is recursive feasibility proved without using robust invariant terminal set? It didn't seem to be defined in the MPC program.
Yeah, that's also a good point. So, so that one is because, it's actually taken care of by this quadratic program. And let me see. Yeah, and the reason that it is completely taken care of by the quadratic program is that by writing down our policies in this way, we can have like a closed loop approximation on every state and every action. And so we can directly impose the constraints on every state and every direction by this polytopic constraints. So it is all buried. So like what you mentioned, the terminal constraints and all those things, they are all buried in this polytopic constraints.
All right, thank you very much, Ying. So I think we should all thank you again for the very nice talk and for answering the questions. And I think that it's time now for a short coffee break. I would say that we start on time with the last talk, Tim, if you agree. Yeah. So we have a 4-minute coffee break. I think also that there is another question in the chat. So Ying, maybe you can respond to that one, typing the answer if it's okay for you. And yeah, we'll see you guys again in 4 minutes time.
See you. Then I guess without further ado, let me introduce our third speaker for today, Florian Dörfler. Florian started engineering cybernetics in Stuttgart way back, then moved to Santa Barbara to do a PhD. Then there was a rather short tenure at UCLA as assistant professor, and now since several years he's at ETH Zurich. And I'm not going to list the many best paper awards and other awards Florian has been receiving, because we want to talk about science here today, and that's a really long list. So without further ado, Florian, the stage is yours, and we're looking forward to your thoughts on data-enabled predictive control.
Perfect. Thank you very much, Tim, for the lovely introduction. Hello, everybody out there in the cyberspace. And of course, it's a pleasure to share the stage with Ying and Pietro, both cherished collaborators. Let me acknowledge the main people behind this talk today. It's mostly my students, Jeremy Colson and Limbin Huang, together with senior collaborators Ivan Markovsky and John Legueros. And by now, we started this research 3 years ago, and now there's quite a long list of contributors, some of which are in the audience, but I'll focus mainly on what these people have done here. So let me start off with some high-level reflections on data-driven control along the lines that Pietro has presented. So when you have no transparent system model, but only data at your disposal, there's two general ways how to attack the problem. The first one is the more conventional, indirect data-driven control way, where you take your data, you do a system modification, you identify a nominal model plus an uncertainty estimate, and you feed that into a robust control pipeline. Another growing trend, especially more recently, is a direct data-driven control, entirely bypassing models where you just design a control policy based on data, which nowadays, as you all know, is quite hyped again. And of course, you wonder why, why should we give up on interpretable models, model-based design? Let me first talk to you about the central promise that these approaches offer, hopefully, which is the quite compelling thought that at the end you're interested in a control policy, and it might be much easier to learn a control policy from data rather than learning a model and then the policy. And this is a trick that control has played all along, ever since the field started, Just think about PID control, a parametric policy, 3 parameters, which can tune very well based on system responses without having a model. In fact, you can do this so well that it got automated already in the 70s. So when is the direct approach actually a viable alternative over the indirect one? So some people would argue based on applications, essentially for some application, the model-based approach is just too complex to be useful. So the models are complex, the ambient environment is complex, you have complicated sensing modalities as perceptions, or hard specifications that you cannot achieve with model-based approaches. And one example is, for instance, soft robotics. Good luck doing anything useful for a model there. Other people quote the shortcoming of system magnification, which are well known, even by the ID people, and have been known for a long time. Namely, system magnification is, of course, cumbersome. It takes a lot of time. And the models you identify to match a fitting criterion, but not for the ultimate purpose, namely control. And often you end up with incompatible uncertainty estimates. And the uncertainty from SysID is typically parametric and stochastic, and what you want for control design is non-parametric and robust uncertainty sets. And finally, we should acknowledge, you can do this only more recently because you have more brute force computational data available. So these are the high-level thoughts. Let me abstract the situation a bit into the math, because I think we can more clearly see things through abstraction. So the indirect model-based approach starts as follows: minimize the control cost depending on input U and state X, which satisfies states with model. Now you don't have the state at your disposal, meaning you have to identify the states from input and output data, U and Y, and of course a model. And finally, the model itself, you also need to identify from offline data from experiments. Let me call the data UD and YD. So at this level of abstraction, you can clearly see that the indirect design pipeline is a nested multi-level optimization problem, where the outermost problem is the control design, the inner problem or the middle problem is the estimation, and innermost is actually then the system identification. Now, for some of these problems, we have a separation principle. Right? You know that under LTR and Gaussianity assumption, you can design your LQR and your Kalman filter separately, piece them together, and it will be optimal. Okay, you can play certain equivalence. Unfortunately, there's no separation principle for the system identification case. You cannot separate identifying a model from what you do with the model later on. And that gave rise to an independent field called ID for control in the 90s. Now, the black box data-driven approach is much more lean. Namely, here just say you want to identify control cost U, Y, okay, depending on inputs and outputs that are consistent with the data that you've seen. So a very lean problem formulation, typically. And at this level of abstraction, you can clearly see the pros and cons. Namely, this above indirect multi-level design pipeline is very modular. Every step is well understood, very tractable, convex, and so on. But it may be end-to-end suboptimal. Reason being, identification does not separate from estimation and control. The lower approach, the direct one, has the potential to be optimal. It's end-to-end, but good luck finding any tractable formulation. And additionally, of course, you want to account for uncertainty in all of this problem formulation. Never take anything at face value. And as you may appreciate, it's very hard to propagate uncertainty in this multi-level problem to push the uncertainty on the data all the way through to the estimation and to the control design and come up with tractable formulations. Typically, you always have to do approximations along the way. Okay, so what I want to present to you today is essentially a direct approach. Okay, and to do so, I'll talk a little bit about non-parametric system theory, particularly behavioral system theory. I'll present you our method called data-enabled predictive control, which in a moment of weakness, we call the deep C. Not because any deep net behind it, it's just we want to make fun of our computer science colleagues. I'll tell you how all of this relates back to system ID, so what's the bridge between direct and indirect, and I'll pepper the talk with some applications from energy robotics. Let me give you just a preview of what this method can do for you. This is sort of my favorite example that we have so far. This is my application domain mostly, it's power systems. You can see it's a large-scale interconnect system. Every circle is a generator. In between, you have some transmission lines that connect them, right? This line is a special one. It's a high-voltage DC link with power converters at both ends that you can modulate to control the grid if you want to. Since the grid is sparse and every of these generators is a rotating device, it's not uncommon to see oscillations, say, between this group of generators and that one. Because if you measure the power flow on the transmission line, this would oscillate. And there will be sustained oscillations, and you want to dampen them. So one thing you can do, you can take the measurements, in the flows of these lines, feed them to your power converters, and then try to dampen these oscillations. And this is a rather tough control problem because the system is large, more than 200 states. We only have 8 measurements. It's nonlinear, stochastic, many timescales involved, so it's stiff. You have input constraints in your controller because you don't want to fry the converters. And in this case, you want to have 2 decentralized controllers, so quite tough specifications. Okay, and you want to dampen these oscillations. And as you can imagine, this is a rather tough control task, especially if you don't have any certificates. Good luck. And what I am after now is, can I do this without a model actually? Which makes a lot of sense in this application because a power system has many owners, generation owners, system operators, and so on. Models are proprietary, and even if you had a model, the grid is changing all the time, so it wouldn't help you at all. So the method I'll present to you now will do the following. It will record about 10 seconds of these oscillations, and then I'll turn on some sort of data-driven predictive control method, which would very quickly dampen these oscillations, actually taking into account all of these complicated specifications, like constraints, nonlinearity, stochasticity, and so on. And what I claim is that this is a method that works reliably. There's not just a lucky shot of one simulation, but I can actually certify to you that yes, it works, and give you the assumption when it works and when it breaks. And I can actually implement it on a microcontroller. Okay, so it's not computationally super expensive. So ideally, this is a method that will get us all the way to essentially making myself unemployed, automating myself. And now you say, well, it's a bit of wacky, like who would ever implement this on a power system and so on? This is the world's most expensive system with, gigawatt-sized actuators. Why would you apply anything data-driven where you don't have any certificates? Turns out some people from Hitachi and ABB actually got to read our papers and implemented this thing. Okay, so this got implemented on industrial R&D simulators. We sent them a piece of black box code, and they implemented it, and it works really well. And so that's now part of their own toolbox and design pipeline. Who knows? Maybe we'll see it in the wild someday. Okay, so just want to give you the flavor. It's not pure theory, it's actually quite useful. Okay, but now I owe you what is behind all of this. So one of the working horses of this approach is behavioral system theory, which was coined by Jan Willems from Groningen. And it's a very abstract branch of system theory that will view a dynamic system just as a set of trajectories. Okay, a very abstract set theoretic definition. In particular, a discrete time system is a 3-tuple consisting of the integers, which form the time axis. We have a signal space where the inputs, outputs, states, and so on will reside. And W to the power of the integers, that's a set of all time series. And the behavior of the system is just a subset of the set of all time series. So you just characterize the set of trajectories by this very abstract set theoretic definition. Surprisingly, can do something with that level of abstractness. We don't need the full power of that. We'll specialize a little more. We namely look at linear systems. And for linear system, your signal space is actually a vector space. And the behavior, the set of all trajectories, is a subspace of the space of all time series. And the system is time invariant. If when you apply the shift operator to any element with behavior and the trajectory, then it's invariant under the shift operator. So here's the picture you have in mind. This here is an LTI system. It's a subspace of the signal space, for instance, space for inputs and outputs. Okay, so just search for subspaces, and it's up to you how you characterize those subspaces. And that's very much resonant to how computer science people think about dynamic systems. They wouldn't think about causality or any sort of parametric representations behind it. They would just look for low-dimensional features in the data set. And this would be such a low-dimensional feature, just a subspace. So what's the takeaway? The only thing you have to remember from this slide is the following. An LTI system is a shift invariant subspace of a trajectory space. And that's what we work with. It's now up to you how you characterize that subspace. You can use a parametric model or raw data. And that's what we're going to do now. In particular, what we do, we use matrix time series, which is sort of the backbone of subspace system ID and some signal processing algorithms to characterize that subspace. So we're given a black box. Okay. We have input data and we have output data that we record. Let's assume the black box is LTI, deterministic for now. Then you know that your data set satisfies an ARX model, some constant coefficient difference equation. Because there's some coefficients B0 times UT, B1 UT plus 1, A0 YT, A1 YT plus US1, so all of it sums up to 0. So let's assume that exists. In behavioral system theory, it's called the kernel representation. Let me show you why. What I could also do, I just collect a whole bunch of these experiments, and I put every experiment in a column of a matrix. So that's the first experiment, first time series, that's the second experiment, it's the third experiment, and so on. So I just put all my experiments in a matrix, okay? And what you may realize now, if you were to multiply the matrix from the left with the vector of coefficients of the ARX model, then you perfectly actually recover the constant coefficient difference equation, meaning this vector is in the left null space and would sort of identify your model. Now the question is, when does this arrow go backwards? Okay, when can you uniquely conclude from a matrix time series based on a model and do something with that? But for this, you need a few assumptions. And these assumptions have become known over time as the so-called fundamental lemma, which was conceived by Jan Willems, Paolo Rappisada, Igor Markovsky, and Bart Dumont in 2005. And we recently, added some extensions that make them necessary and sufficient. The setup is the following. What we have is we're given data again from an LTI system. U is in RM, Y is in RP. And we assume we know some complexity specifications, or at least upper bounds on how complex is the LTI system. So an upper bound on the order, so the number of states in minimal realization, N. And we know an upper bound on the lag, that is how many time steps you have to go backwards to compute an initial condition. So of course, in the single input, single output case, these two guys are the same, L is N, but in the MIMO case, this can be different. Then we take the set theoretic perspective. So we look at the set of all trajectories of finite length, in this case, length t, set of all u, y in Rm plus pt, that satisfies state space model, for instance. So they exist in X, so that X plus is X plus du, Y is Cx plus du. So this is a parametric way of describing the behavior, a set of trajectories. And what I claim now is you can also have a non-parametric representation. If you want to call it a model representation, it's up to you. But what you can do, you can just pile up all your data into a matrix, okay? Experiment 1, experiment 2, experiment 3, and so on. And the span of these columns, the column span of the matrix, is equal to the set of all t-length trajectories. Okay, so this is completely non-parametric, based on raw data. Call the model not, I guess that's terminology. But that's quite nice. So that's almost too good to be true. Of course, there are some assumptions in place. And the assumptions are the following. So this is true if and only if this matrix here is of low rank. Okay? In particular, we assume that matrix has rank m, number of inputs, times t, the length of the time series, plus n, the number of states behind the model, for all t which are longer than the lag of the system. Okay. So if you don't remember anything from this talk now, this is about the only thing you remember. If you're interested in the behavior of the system, you can just work with raw data. No need to go to parametric models. Okay, just work with the linear span of a bunch of time series. And in words, it means all trajectories you ever want to construct, you can construct from finitely many previous trajectories. You can also use other matrix data structures. So it may be more efficient to use something like a Hankel structure or mosaic Hankel or whatsoever. And you wonder, why is this result called the fundamental lemma? To some extent, many other methods out there, like motion primitives, dynamic mode decomposition, dictionary learning, explicitly, blah, 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 all rely on matrix time series, but nobody actually has ever established that equivalence until that 2005 paper. That's, I guess, why it deserves the name fundamental. I don't take really credit for that result. It's really due to this paper from 2005. That the result was only sufficient with a bunch of extra assumptions, which were removed. And from here, an entire literature starts bifurcating. That result has been more or less forgotten for 20 years and got sort of lifted up back in the spotlight about 3 years ago. And now a lot of people are working on this. Actually, I think quite a lot of people in the audience here have contributed to the recent literature on, making this result useful, say for predictive control or for explicit feedback policies. So there's a quite blooming literature with about 2 to 3 papers per week by now coming out. And particularly, I want to acknowledge the sort of work on explicit control design based on this fundamental lemma, based from, from my colleagues in Kroning and like Pedro and others. But what we'll do now is we don't go into the explicit control. We use this now as a constraint in an optimization problem to find optimal controllers. So let me quickly review output model predictive control, MPC, which goes as follows. You give yourself a stage cost So you have tracking y minus a reference r squared plus input penalty squared, summing of all stages up to t future, which is your prediction horizon. You have constraints on every stage. So for instance, saturation of inputs and so on. And what you need to do, you need to forward propagate your dynamics. So you need to do prediction. So you write down your ABCD state space equation and propagate them forwards. And index k runs now forward in time for the prediction. Now, of course, this doesn't quite work out that way, because even though you may see it in papers, in practice, a non-trivial issue is they need an initial condition for that recursion. That is, you need to measure the state. If you cannot measure the state, you need to estimate. So one way to estimate the state in an MPC context is using a moving horizon estimation. That is, what you do, use again your model ABCD, but now the time index runs backwards in time. So it runs from 0, -1, until some minus t minus 1, where the estimation horizon is sufficiently long. It must be longer than the lag of the systems. And there's many variations of flavors, so you can write this down. In particular, if you have any sort of observation noise on your measurements, you want to solve this equation in a least square fashion, and so you do some sort of MPC version of Kalman filtering. And now you call that optimization problem, you get an optimal control policy, you get new measurements, refresh, call it again, so you solve this in a receding horizon fashion. Now, this may not be the most elegant approach to control design because you outsource the problem to a computer, but we should all acknowledge that, this works really well. And computers will always win, if not today, then tomorrow. In particular, this is really the gold standard of control. Assuming your plant is deterministic, it's LTI, and you have a model, then you can't beat this. Okay, it will be as good as it gets. Now we have to worry about what if the plant is not deterministic, if it's not linear, and if you don't have a model. Okay, so that's what this talk will be about. And now I want to present you this data-enabled predictive control, the deep C. And what it does, essentially, it replaces the ABCD system that you use for prediction estimation by this fundamental lemma. You say any trajectory must live in the image of the trajectory matrix. That is, there exists a vector G that collects all the columns of that matrix to form a new trajectory. And what is that new trajectory? It's a concatenation of the estimation you have. So that's the last few measurements you have, the U, INI, and YINI that you use to estimate an initial condition. So you update these online. And that's the future U and Y that you predict over. So that's just one trajectory consisting of measurements and prediction. And now you optimize whether the vector G that takes into account the linear columns here. And this data for the trajectory matrix you get offline from experiments. Now, it's not so hard to show formally that this is actually equivalent to NPC in the deterministic LTI case. And a lot of things you know about NPC you can now map over. I refer to the group in Stuttgart that mapped over a lot of the stability and robustness properties of NPC to this data-driven NPC. But it turns out when you have either noise or nonlinearity, then this doesn't work. You need to robustify it one way or another. Okay. Maybe let me show you a quick experiment, how we get it to work when we have to robustify it. So here's a quadcopter in our lab. We fly the quadcopter now by hand, so we fly it manually. So we use that manual flight essentially to build up this trajectory matrix. So now we have our data. And now we run this deep C to track now figure 8. And it would work really well without, at any point in time, there was no model involved. It's completely data-driven. So somehow we can get it to work, and let me now show you the tricks how you can get it to work. The first thing you have to worry about is that the real-time measurements are noisy. Okay? So what you need to do, you need to somehow do some sort of Kalman filtering on the real-time measurements. The MPC version of doing this, you add a slack variable, sigma ini, and you solve for the least slack solution. So say you add some sigma ini squared penalty here with some multiplier on the y, and you can think about this as an exact penalty formulation. Let's run some sensitivity Monte Carlo simulations on our quadcopter example. You can actually see as we increase the multiplier here in front of the slack variable, the cost will go down, and the constraint violations will also nicely go down. So this works well. But that's the easy case. The harder case is, of course, your data itself may also be corrupted by noise. Okay? How do you do with that? I mean, that's multiplicative noise, or as statisticians call it, it's the error in variable setup. We tried a lot of things. Many things don't work that you think might work. But let me show you one thing that works. Namely, there's many solutions G to that equation. And now we regularize the problem to find a particular solution G. In particular, what I add here is a 1 norm on G with some multiplier lambda G. So why would you do this? I'll give you the theory later on, but let me now just tell you the intuition. What does L1 do? It would sparsely select columns of this trajectory matrix. So it would sparsely select motion primitives based on which you synthesize the optimal trajectories that constructs a low order basis for the behavior. Yep. And again, you can try this out. In the quadcopter, you see the cost goes down, constraint violations go down as you increase that multiplier, and eventually, of course, you over-regularize and things will go up again. But for a quite large set of regularizers, this works really well. Now, let me give you a little bit of theory behind that. And the theory I use now, we have different explanations. I use bi-level optimization, okay, because I guess this is the optimal control seminar, so I should do optimization. So in particular, you can send the regularization as a relaxation of the bi-level system identification and control problem. So just recall the problem formulation. This would be the data-driven control, okay? Where you say your U and your Y should be an image of the trajectory matrix, and there's a vector G that you select, okay? But that trajectory matrix itself is corrupted by noise. So you first want to identify a proper matrix, in this case, a non-parametric model representation. So what I want to have an inner problem, which says, well, this trajectory matrix is the closest approximation, so an argument, to a matrix that has the desired rank. It has the low rank feature. Because if I have a low rank trajectory matrix, then there's a one-to-one connection to an LTI model. So there's essentially an inner rank constraint, which accounts for model order selection, and you project on that rank constraint, so you find the closest set of data that would correspond to an LTI model. So this is a bi-level optimization problem, and what I want to show you now is actually with quite easy math, how you can lift this to the problem you've just seen. So let's go through a sequence of convex relaxations. The first thing I'll do here, I add to this problem without less functionality, constraint on G. You know, if this guy here is low rank, then also the G here I can choose it with at most ML plus N entries. So the cardinality of G is at most ML plus N. Next, I don't like rank constraints. Oh, sorry. Now here it is again. I don't like rank constraints. They're non-convex, so I'll just cross it out. Let me remove the rank constraint. But if I remove the rank constraint, then this has a unique solution. Then, you know, this is triggered in a problem. Then it's just the data you see. So you take the data at face value. So I'm now here. And now I don't like the cardinality constraint either. Let me also relax that to a one norm constraint. So that's another relaxation. And finally, let me lift that one norm constraint with an exact penalty just to the cost function and say there's some multiplier lambda G, which corresponds to the dual variable here, times a one norm. And so that the takeaway is, that's this regularized DPC formulation you've seen. And what you see now, this L1 regularization is really just a convex relaxation of the non-convex system identification step. Particularly, the regularizer smoothens out the model order selection, which is very good for you because that means you don't encounter bias error when you select the wrong model order. Okay? So you never project the data onto any model class as you would do here. You just regularize it to promote the model class. It turns out I can also do this when I put here different identification problems. So when I put here, instead of this, I put here a least square identification problem, exactly the one that Pietro has shown, just an input-output setting. So if I find a parametric predictor using least squares that says Y is some linear map K that relates your U and your past data. So essentially, the K is the matrix of Markov parameters. So C, A to the K, B. Okay. This matrix generally is low rank, has constant sparsity and correlated entries. If I now again go through a sequence of convex relaxations and I drop the rank, sparsity, and correlation, then I get more or less the regularized that Pietro has shown to you. I get something where I project on the kernel of this trajectory matrix. Okay, more or less exactly the same as Pietro has shown to you. Which has some interesting properties. If you use, for instance, that regularizer compared to just a pure norm-based regularizer, and I show you the performance, the realized performance closed loop, it would actually not have this behavior of a normal regularizer that you eventually over-regularize. Now it would actually stay flat here, which is a very desirable feature because that means you don't have to tune the regularizer, just pick it sufficiently large and you gain. Okay, so that's very nice for optimization result. Okay, so now we understand how we can derive all of this from a bi-level system ID and control. How do we apply it to nonlinear systems? And we're pragmatic. We just say every system is linear without loss of generality. And it's actually an accurate statement because there's various tricks in the books like Kahneman linearization, Volterra-Flies, time series, Koopman operators, and so on, that allow you to lift a nonlinear system under some assumption to a large dimensional, typically infinite dimensional linear system, sometimes bilinear in the input. More pragmatically, you would say, well, give me any nonlinear dynamics on a finite time horizon, I can approximate an arbitrary world by a sufficiently high order LTI system. So let's just do this. Let's collect more data. And let's hope that the regularization will figure out what are the relevant features in the data. And it works for many examples. And so we've drawn this essentially in every example we found in our lab. So you've already seen the quadcopter, we saw the power system, but we also had others like building automation, power converters, drives, and we even put it in a 12-ton excavator, where we had essentially excavator digging based on data, which was quite interesting. And of course, it's not practically useful. It's just for us a really interesting benchmark example. But you can do this. And it really works out in all these case studies, some of which are quite nonlinear. And we should understand why it works out so well. And I can just tell you what the understanding is so far. What helps if you adopt a slightly stochastic formulation of the problem, which explains to you why does this regularization work out so well when you look at it from a stochastic lens. In particular, we call upon DRO, distributional robustness. So on an abstract level, the optimization problem we want to solve is minimize the decision of x over a cost function called graphic x, feasible set x, cost function c, that depends on measured data, on samples. And these samples are not a truthful representation of reality, they're just samples. There are many realities that are compatible with the samples. So what you need to do, you need to robustify yourself for the fact that the samples are not a truthful representation of reality. And without going into many mathematical details, what we do, we solve a min-max problem. And what is that max about? We maximize over all stochastic processes, which are linear, maybe nonlinear, maybe Gaussian, maybe non-Gaussian, maybe stationary, maybe non-stationary, whatever. All processes that could have generated these samples, okay? And so we're robust to the data generating process. How do we write this down mathematically? What does this mean? We write down an inf soup problem, and we replace the cost function here by an expected value of the cost, where the expectation is with respect to an unknown probability distribution Q. We don't know the probability distribution that has given rise to the samples. We just know that it's nearby to our sample distribution. So that's the distribution give rise to the samples. P hat is just a delta for every sample. And we say we want to be epsilon close to the sample distribution, okay? And what is the metric that we put on the ball? It's the Wasserstein metric. So if you want, you can look at the formula or the picture. What's the distance between two distributions? Say the sample distribution and another one. We essentially count how much work does it take you to get this third pile and that third pile. So you take the xi hat and the xi, you take the difference between the two, some p norm, and then take the expected value over the joint distribution pi, which has the right marginals on both axes. And there are many such distributions, so you take the one that gives you the smallest cost. And then you write down this inf soup problem. Now, of course, this looks horrible, like a doubly semi-infinite problem. It turns out you can actually resolve it on a very minor assumption. I guess you only need Lipschitzness of the cost. And then it turns out that this nasty inf soup problem will recover your original problem, the one that you just solved with the samples, plus a regularizer. And you regularize with the uncertainty estimate, epsilon, how big should your ball be, times the Lipschitz constant, times the dual norm of what you put here. Meaning if I put here, say, an infinity norm, so I want infinity robustness of vector space, then I need to regularize with the L1 norm, which is quite neat. So now you understand why we're not taking account really nonlinearity, but we're robustifying ourselves to nonlinearity. We're robust to all nearby data generating systems in L infinity norm and the trajectory space. Okay, and that's sort of my best explanation by now why it works so well. There's some further results, which I could spend another hour talking about. Let me skip those. Maybe just one last thought. How does all of this relate to sequential system ID and control? I already told you can derive it as a relaxation of system ID and control. Now, what is surprising, in every single experimental case study we looked at, we always beat system ID and control. Let me be more precise, we always beat identification of a linear system and certain equivalence control. And that's something to be understood. Why? And let me just tell you in one last slide why I think this is the case. So let me go back to our bi-level problem formulation, the indirect control. Find a controller where U and Y satisfy a parametric model, and the model you identify from some identification problem, subject to the model being in a class of LTI system, specified by some order n and some lag L. So what is this inner ID doing when you think about it? It does the following. The ID projects data on the set of LTI models with complexity parameters, n and L. This projection, of course, removes the noise. So you remove variance, you lower the variance error. But when you project on something, you better know what to project on. Because if the system is not LTI, or if it is LTI, but with different complexity errors, then you suffer here a major bias error. Okay, so if you have a bias error in your identification, then this indirect approach will inevitably always lose, in particular for nonlinear systems. Whereas the direct approach doesn't have any projection of data onto anything. It just promotes through the regularizer here some sort of low order behavior. And the choosing regularizer makes it work. You don't get any denoising, but you also don't get any bias. Okay, and this is my understanding why we actually always beat linear identification and control. Let me jump straight to the conclusion slide. Here's the summary. I will not repeat that. In terms of ongoing work, as you saw, we are robust to nonlinearity, but we want to truly understand nonlinear systems. We want to understand the adaptive control case, so when you update the data online, and of course, go to application of true business case. And finally, I should emphasize, there's no free lunch. There's a catch to everything. And the catch here is when you go the database way, the optimization problems you have to solve in real time become bigger than when you go the model-based way. Not prohibitively, we can still solve them, but that reveals the model sort of compressed and tidied up denoised representations. Thank you very much, and let me know if you have any questions.
Thank you, Florian, for a very nice talk and a big round of virtual applause. And we already have 2 questions in the Q&A tab. And I would first start with Darius. He's asking, is there any chance to generalize this to continuous time systems and maybe even nonlinear continuous time systems? Any thoughts on this?
I have not thought about the continuous time case. But also for the continuous time case, what should be true is that when you assemble your time series, there should be a low rank behavior in some sense. If you think about an autonomous system, at most the time series can have rank n, which is the dimensionality of the initial condition. But I have never thought about the continuous time case. I've never seen anybody who actually did that. At most, people work with sample data systems. About the nonlinear case, there are various people that worked on various directions on how to generalize that. Let me just give you maybe the main ideas. Let's scroll back to that slide here. So in the nonlinear case, you can take the approach that you just assume that there's a very large scale linear model behind it. So one that probably has a very large n, okay? Because if you go to sufficiently high dimensional models, they can explain everything. Alternatively, what you can do, you can feed your measurements through feature map. That means you don't just take U and Y, but you also take U squared and Y squared, and then build up your trajectory library using these polynomial feature maps. In either case, you will inevitably run into the curse of dimensionality. I've not yet seen a better approach, but I know there's at least 10 groups working on it.
Thanks, Florian. And here's directly the next one from Sung Ho, who's referring to one of your concluding remarks. How do you manage the tractability of the optimization problem in terms of the Hankel matrices growing very large if you feed in a lot of data? And do you have any comment on the number of data that you need versus the performance you get, especially under a noisy setting?
Sure. So there's a minimum number of data points that you need, which you need for this rank condition. Namely, the rank of the matrix has to be m times your prediction plus your estimation horizon plus n. Typically, what we observe empirically is when you have more data, it works better. but only up to a certain point. Typically, when the matrix is square, that's when performance plateaus. Meaning what we do in practice, we collect enough data so that the Hankel matrix or trajectory matrix, whatever you want to use, is square. And what we do then, when we get more data, we average data, because under some assumptions on the underlying distribution, like it's low-tailed, you can show that averaging sort of removes variance. So if you get more data, we just keep on averaging, and that's how we keep the size of the data matrix bounded, and thus also the size of the optimization problem. Now, of course, when we implement this, say, on a microcontroller, for instance, in the power electronics implementations on a DSP, which has essentially, I don't know, no memory and nothing, we cannot solve this problem in real time. Real time meaning here 10 kilohertz frequency when you solve the optimization problems, so very, very fast. There we resort to some tricks similar to explicit MPC. That is, we pre-parameterize the solution set as linear affine maps and then use those. But that gets you very close to essentially a priori learning a model. So I'm not sure that's the way to go. But yeah, the price to pay is more computation.
Yeah. Thanks for the answer. And then we have the next question from Rafał Wisniewski. Concerning the study of nonlinear systems using the linear infinite dimensional approach, the knowledge of the basis of the linear operator seems to be necessary. But how to get this information from the available data? Do you have any hint?
I wish I had one. That's the question, isn't it?
That's what Koopman hasn't told us, I would say.
Yes, correct. So either you just construct a sufficiently general basis like polynomial or Fourier terms, which can express any continuous function and then work with that. But then, of course, you run into cursive dimensionality. What may work better, and I know some groups are working on this, is to use kernel-based approaches. That is, if you work out the explicit solution of this optimization problem, you see it goes like inner products of the columns of the data matrix, and then you replace these inner products not by feature maps, as you suggest, but replace them by something like kernels from Gaussian processes or so, like square exponential kernels. Then you're much more expressive. Of course, the price to pay again is you need to invert large matrices. That is more computation. But that's the big open problem, and a lot of people are working on it.
Yep, I agree. And here we have a question from Joao. Could one use the maximum entropy formulation of Zaridis that establishes an equivalence between entropy and cost to in turn establish a relation between the performance of DPC and indirect adaptive control?
I have to confess that's the first time I hear that. I don't have any smart thoughts on this, but of course I would love to follow up on that. I don't have anything clever to say, to be honest. But yes, the way we do this, sort of the brute force way, I'm sure there are some clever shortcuts.
Yep. Okay, and there's a follow-up, which I'm not sure whether you have already covered it, but nevertheless, I'll ask you from Joao again. How conservative is the certification with respect to stability and or performance of DPC?
So formal certificates say if you go for the distributional robust way, where is it? Say here. So what is it about? That you need to choose this epsilon. You want to be robust to all epsilon nearby time series in this particular metric. And certifying it means, can you quantify that epsilon based on the data you've seen? It turns out, yes, you can. There are some statistical formulas that tell you how this epsilon actually should go to zero, the more data you get. It turns out these formulas are like doubly exponential. So they're more like existential formulas. They're not very useful. The way you do it in practice is just cross-validation. So that's all I can say here.
Yep, thanks. And then we have a question from Zhenggang. Thanks a lot for the great talk. I have a question about the distributionally robust control. And sub-question 1, should the objective function in this work be concave in the uncertainty to reformulate the DRO problem with the Wasserstein ball to a tractable convex program? And B, any chance to apply any other metric or divergence from DRO in distributionally robust control in terms of reformulating a tractable optimization problem?
Yes, both great questions. So they're more or less about where does this equivalence come from? Why can you replace the inner max with a norm-based regularizer? It turns out the problem does not have any nice convexity concavity properties. But if you work through this reformulation here, or through this maximum in closed form, you first go to the Kantorovich dual formulation, and then you go through a whole bunch of convex conjugates. You can, after like 3 pages of tedious by hand calculation, work out that there's this regularizer coming out. Okay, so there's no shortcut in terms of exploiting convexity concavity. What about when you put here a more general cost function, not just a norm? I know a lot of people in the DRO community are working on extending this. For instance, it turns out for certain sort of distance function you put here, you don't regularize with the norm, but say with the gradient of the objective function. That's just not a thing that comes out. So there is a lot of active work on DRO, how depending on what you choose here, you get different regularizers. I would refer to the work of Daniel Kuhn and EPFL. He has a string of papers on that topic. We were mostly using it sort of as an a posteriori justification. That is, we wanted to understand where does this regularizer come from, and we found this was a very nice theory that explained that regularizer. But of course, now you can also develop others.
Okay, and here directly comes the next question by Johannes Teutsch. Thanks for the nice talk. I have a question regarding the use of the slack variable. In case of noisy data, why is it beneficial to use the slack variable to account for the resulting error? And as far as he can see, there's no guarantee that Willem's fundamental lemma is recovered. That is, the slack variable absorbs the error resulting from the noise. Wouldn't it be sufficient to only regularize the parameter G into cost in this case?
Mm-hmm. So those are multiple questions at once. Let me answer the last one first. It's not sufficient if you regularize G. That doesn't work. The reason being, if your real-time measurements are noisy, then these first two equations will be infeasible. They may not lie in the image of that matrix. Okay. In order for this measurements to lie in the image of that matrix, you need to add the slack variable. And then we solve for the least slack. Okay. In the model-based way, you can understand this as sort of a finite horizon type Kalman filter, solve the least square estimation problem, for instance. Now, on the second question you asked, so that answers the third and the first. On the second, does Willem's fundamental lemma give you any guarantees on that? No, it doesn't give you anything. It's the way the result is, plainly stated. It's meant to be a result for LTI systems deterministic. That is, you can use your trajectory set as a predictor only when you have deterministic systems, and what is really below this is this rank constraint. Okay, only for deterministic LTI system you have that rank constraint. Now, of course, various people, among others people in the audience, Timm, for instance, have worked out nonlinear or stochastic versions in particular cases under particular assumptions for this equivalence here. That is, you know, if you have a different system class, not deterministic LTI, what other result may you derive? So there's some work on that.
Okay, thanks. And then we have, I think, the second to last question. We keep you busy today, Florian. Yeah. In the LTI stochastic case, you solved the relaxed optimization problem involving the L1 norm and the drop of the rank constraint. How can you ensure that this is a solution also to the original problem? Or is it not even necessary to ensure that you get a solution of the original problem?
Yes, so that refers to here. I guess what I'm doing here, I cancel out the rank constraint, meaning now the optimization problem that I solve does not have an underlying constraint that there's a finite dimensional LTI system behind it anymore. Meaning I just have big time enlarge my feasible set, and the solution I get may not be feasible. You're absolutely right. But you can still apply the controller, and actually we have some upper bounds on the worst case performance that you may encounter. Okay. So it's not like you're completely open loop. You have some worst case guarantees in terms of what may happen. What you do with constraints, it turns out, that's another thing I've skipped. When you do the relaxation, for instance, you motivated by the L1 regularization here from the DRO, you're robust to all nearby systems. you can apply the same type of in super formulation to constraints. Say you have probabilistic constraints like a conditional value at risk, a CVAR, you do a DRO CVAR. Okay, so you have the CVAR with respect to the worst case distribution that may have given you rise to the data, and you can play similar tricks to replace the DRO CVAR constraint by a relaxed constraint. But in general, everything I said today was about the optimization formulation. I didn't make any hard statement about the closed loop. So.
Okay, so we see another open problem for future research for all of us.
Yes.
Analyzing the closed loop in this setting. And we have a final question in the chat from Deepak. In your experience, Florian, how big is the Hankel matrix for model identification, or how many data points are needed? And how is it complicated to handle the Hankel matrix?
So when I talk to people like my colleague Roy Smith here across the hallway, who have done a lot of empirical system identification, that is, identified real world systems, they would also confirm that typically you pick this Hankel matrix to be square. I have not fully understood yet if there's a theoretical reason and numerical reason behind it, but it seems like both in our formulation as well as in SysID formulation, you typically get best performance if you pick the matrix square, and if more data, you just keep on averaging it.
Okay, I think that was the final question. We are perfectly in line with our agenda, and I give the word back to Thulasi.
Thanks, Tim. Thank you to all the speakers. So we have essentially now around 10 minutes for if there are any general questions also among the panelists, the speakers. So yeah, if you have anything at all that you would like to discuss based on the 3 talks that we've seen, feel free to write in the chat, or for you speakers as well, you can just unmute yourself and speak.
That's always the tricky bit of virtual seminars. Whether there is a general debate at the end or not. But we just felt like without having it, it's a bit rude to then just say, okay, goodbye, bam, and we're offline again. So, but if there's not, let's say, generic.
I can throw in a controversial question for everybody.
Yes, please, Florian, do.
Namely, I have fun playing these data-driven games, but I have not yet seen a business case for that. That is, I still have to convince myself of any, system, class, or real-world practical problem where you would go the data-driven way. You can, of course, and we've seen plenty of examples, but when would you really do it this way and not the model-based way? Anybody has a compelling example for me?
Actually, what I would have thrown back at you, tempting an answer, would have been energy systems. If you want to schedule a large set of distributed energy resources, how it's called in the power systems world, then you're happy if you don't have to hire someone very well educated who does the SysID for each single battery in each single Tesla car in front of each single home. This is why I think that could play out nicely. And of course, you could say, hey, but I could automate this SysID. I think, truth to be told, yeah, there's a trade-off.
That's also what I heard from the people that implemented our method. They said it saves time for the commissioning engineer. You don't need a tuner anymore. Yes, but you also lose a lot of things, right? In particular, you lose interpretability of what you do.
Right. But to a certain extent, advanced control systems always lack interpretability for let's say, for the brownfield engineer who's going to implement it, right? There's always a trade-off there, at least from my understanding. But maybe someone else wants to add in this regard? If that's not
I may add
Pietro, please.
an example based on my experience with a collaboration with the Italian National Institute for Astrophysics in the design of a real-time controller for ground-based telescopes. And in that application, identifying a model is not only basically prohibitive, but it's also useless. It's so complicated, the model that you get. Essentially, what they do is just PID control, and they want a data-driven method to tune them.
Mhm.
So it's not about the impossibility of getting a modeler, it's also about the model that you get. I mean, you have no model-based control technique.
Mhm.
That's my experience. Yeah.
But maybe what is underlying your question, Florian, is the question for a set of real-world benchmark examples for data-driven control, for the different facets, how you could go about it. I mean, with realistic data sets and realistic, let's say, requirements for how the controller should perform, that could be something interesting to compile or to put together.
Right, yeah, definitely. I mean, what I would be interested in are problems such as the one that Pietro mentioned, where model-based control is just hopeless. Another example is, of course, soft robotics, like a robotic hand or so, made of soft material, where models are useless, and where you could not try out such methods if they would get you anything at all.
Okay, are there further comments or remarks at this point? Eric Kerrigan in the Q&A tab. Eric, I'll read out your question. Eric writes, people often tell me the problem with MPC is that you need a model. For database control, the problem is that you need data. So when is a model good enough for control, or when is data good enough for control? Any thoughts on this from our speakers? Great question, Eric.
So in all applications where we applied our method, essentially applications were open loop stable. That is, we could experiment with the model and collect the data, or we were flying the quadcopter by hand. Now, this would be impossible, of course, if your system is open loop unstable, right? Then all of this, the theory would work, but the practice, you wouldn't do this anyways. So it's a good question. Where do you get the data from, right? Essentially, you need a pre-stabilized system or an open loop stable system.
Okay, so are there further questions? If that's not the case, I think it's time for a final round of applause for all our three speakers. Very good talks. I really enjoyed it very much, today's seminar. Thanks a lot. And thanks also to the audience for the very interesting questions. And as a concluding remark, Thulasi and me are organizing this seminar, but if you have any suggestion for what kind of topic we should cover next or which speakers to involve, feel free to drop Thulasi or me a line. We are happy to compile the next seminar. We try to have 2 of those seminars per year. So we are very open for suggestions for the next topics to cover. Yeah. And with this, thanks a lot for your attendance.
Thank you very much.